Okay, good afternoon everybody. So I am Debopam Das. I teach fluid mechanics, mainly fluid mechanics or related subject, and I just know that here different branch people are there, but is there all civil and mechanical people here, or mechanical and civil are there? Biotech, computer science, electronics, all are there. Okay, but the talk that I have prepared is in terms of how we teach fluid mechanics. Okay. So, that is mostly probably directly relevant to the people who are teaching fluid mechanics. All of you are faculty, I am also a faculty. So, we are all like colleagues. So, it is just the kind of way we do it and kind of way you do it. If the mutual discussion can help us, that is the way I see this class. So, the electronics and computer science people, those who are here, those faculty members who are here, they probably can get a little bored, but I will try to make it a little interesting also, but I do not know how much you will be, because I have focused it only in terms of teaching in fluid mechanics, which is the title given in this talk. So, fluid mechanics is a big subject. So, you will see that there will be undergraduate level fluid mechanics, then again you do a postgraduate level fluid mechanics, and you can do other advanced level fluid mechanics like aerospace, or even mechanical people will be doing gas dynamics, which is specially related to gas, where you can compress the fluid and things like that. But in this case, what I am going to focus on is the undergraduate students teaching. How many of you are teaching postgraduate in your place? None. Okay. So, that is why the focus is undergraduate, because that is the information I had got, and so I am not I am going to talk about purely on this undergraduate fluid mechanics teaching part. Okay. So, generally textbook that I follow is following textbooks, which is this textbook is probably the ideal undergraduate textbook. A similar textbook is this one. Okay. This is slightly advanced, slightly more precise kind of brief writing you will see. It is written by one civil engineering professor from MIT, Professor Fay, after his retirement. So, with all his experience he has written. So, it will be that way quite interesting, and many concepts can be very clearly means it gets cleared when you read this book also. And this is one of the book which many of the institute we use, which has a good collection of problems, but as far as theory part is concerned, I think these books will be much more interesting thing. So, in undergraduate we all know what we teach. So, I just I am giving you, like, when I have taught 4 times here our big class here in IIT Kanpur. We teach all the branches, including computer science, electrical, or whatever branches we have. Anybody who wants to take, some department students have to compulsorily take this course, or some department they can take it optional. They have to take some such compulsory courses. So, that is the second year level course where we teach the following things. So, as a syllabus we all talk about the continuum, and then we define different properties. Then the fluid statics, which is usually the first step in teaching fluid dynamics, and then we start from the statics, then we go to kinematics, and then slowly we go to the dynamics. So, fluid static, kinematics, then this RTT is what? Reynolds transport theorem. So, the Reynolds transport theorem and conservation of mass, linear momentum, and when required, when we are talking about turbo machines and all, angular momentum we talk about. Then we derive the Navier-Stokes equation, but we also talk about Bernoulli's equation and the energy equation quite extensively in a UG course. We do not talk so much about Navier-Stokes equation probably, but we do introduce Navier-Stokes equation and do some exact solution of Navier-Stokes equation in this second year level course. Okay. So, this is required because after that we look into the losses related to this energy equation when we see losses in pipe flows and all long pipelines and all. So, and all the minor losses that you observe that I will talk about little bit. This dimension analysis is one of the important topic that we cover. Then we cover potential flow, little bit of boundary layer introduction we do in the second year level itself. Okay. So, this is usually what we cover, and we talk about, to make this a little interesting, we talk about this boundary layer separation and things like that, where we just need the qualitative knowledge and things like that. So, usually each fluid dynamics course, here you neglect these dates. I have kept it intentionally, this slide with the dates. Usually this course we will have tutorial class. So, which is basically a problem solving class. So, every week after teaching, I will be giving the students a set of problems on that particular topics that we have covered, and then I do not know whether you get TAs for or not. Many times here, because it is a very large class, so it is divided into about 35-40 students class tutorial. So, out of let us say 100 students or 400 students, about 10-12 tutorial will be there, which is a smaller class, which is precisely they meet once in a week for problem solving. Okay. So, that problem solving, like we have to decide. So, as an instructor I have to know that okay, this week we are going to do this problem solving, this week we are going to do this problem solving. So, this is some 2012 or something I did teaching, and that is the time in the beginning itself I have to make all this assignments or the problem solving assignments, and then they will be solving and they will come and discuss with the tutor. Tutor will be some other faculty members. Okay. So, can be even the PhD students who are senior level PhD students, they can also be, and then they will solve this problem in the class and discuss about the problem. This is how we go as far as problem solving part is concerned, which is a part of our tutorial thing. Now, fluid mechanics is a subject which I have seen as many students, they will be afraid of this subject, and it is when you make it interesting, you will see many students wants to do fluid mechanics. So, this is the job as a teacher, probably our job is to motivate the student to make them interesting, and I will be focusing mostly some of these salient features. It is not possible to cover all these topics in this 40 minutes lecture. I am just going to give some salient features of this course which I covered, which I think that is required, and if we address that properly, then the students' doubt gets cleared. But in the beginning I try to motivate the students, okay? And to motivate the students I talk about this, what this fluid mechanics applications that you see in different field, starting from automobile engines, aircraft, vessels, pipe networks, fluidic devices. Sports ball is a very interesting thing where all the young kids gets interested when you start talking about how cricket ball swings and things like that, and then you can also bring it in the some of this biological this thing I will show you. So, it is actually a subject where you can see many attractive spectacular pictures you can generate, whether you do computation or whether you do experiment. You can generate many spectacular pictures, and these spectacular pictures are actually which that create the interest among the students, that why this happens, how it happens. In this particular one drop, assuming a raindrop falling in a lake, and how the liquid sheet is going up, why there are so many waves, and why then there is this fingering kind of thing which eventually breaks up into small spherical droplets. So, all these questions will come when you observe things and such a spectacular things, and many such spectacular things can be possible to show in fluid mechanics, which computer science people they do in their visual simulation also. Okay. So, which they can do using some problem. This is so they can do using their using this fluid dynamics equations also. So, in the beginning when I start the class, my first class goes in this motivational this thing, where I bring different examples, where you can see this is a dye visualization flow past a car. Okay. This is taken from this thing. Okay. Most of these pictures are taken from different sources, which are not all listed here, and if anybody interested can get it from me. Now, you can see that when I show this picture, then a student will have the idea how the flow over a car looks like, and you can immediately show that, see, there is a very nice attached flow over this car, where this dye is not getting mixed, but in this region it is getting mixed. Okay. So, this region of flow we can largely call laminar flow, whereas this region it is turbulent flow or transitional flow. If you see this over a blub body, again a similar thing happens. You have a nice laminar flow, but then you have some transitional flow or vortex, this kind of thing forms. If you see this particular picture, this is aircraft when it moves, it is landing. At that time, near the wing tip, you see such a large recirculating flow generates. Okay. What is its implication? It has its implication which actually enhances the drag, in the sense that you require more energy to drive at that because of this vortex, because this vortex is formed due to the motion of this wing, and if this has formed, this fluid has got some energy. Where from it? It has some kinetic energy or rotational energy it has got. Where from it got this energy? So, this energy must have been spent by this engine. So, it actually results some additional drag to this. So, this kind of now this is a cycle. You can see the helmet position here and helmet position here. So, you can see that this helmet positions, this will increase the drag, whereas this will be. So, many times you will be seeing that cycling when the people do the racing cycle, particularly the competitions and all, they will be keeping their head like this, because that is the drag there, less drag you will observe. These are mostly the engineering applications, where you can see here, this is a long bridge in San Francisco, and you can see that this wakes are visible from each of these supports pillars. You can see these wakes are forming. Okay. And this is in an island where you can see the low clouds. When they are in the low, again you have this recirculating flow which you are observing. Okay. This is called Karman vortex street, which if you keep a circular object and if you pass the flow from left to right in this picture, then you will see this nice vortices forming, nice structure will be forming, which is you see in practice here also, which in laboratory we generate nicely. Here also you will see in this kind of thing. Well, you can see this similarity in these two flows. You can see the waves that are formed when this particular boat is moving, and the waves when this duck is moving. The waves, you will see certain differences, you will see certain similarities in this kind of situations. This is a aircraft T-38 moving at Mach 1.1, very old image, and you can see there are sharp lines here. Those who are in fluid mechanics, you all know that these are shocks which are forming from these surfaces at different locations. So, this is and this region is the wake region. You also see application of the fluid mechanics. From the heart, when we observe this our circulatory system, flow in our circulatory system or flow in our respiratory system, it is entirely fluid mechanics. And most of the research, when you will be seeing, you will see that from the heart this how the fluid is going out, and because of the systole and diastole or the heart pumping. And then if there is a bifurcation, how the cholesterol deposition and all these things happens there. All these modern studies that is going on, it's involved fluid mechanics. So, and the biology people will be very much involved in this kind of thing, but it's basically understanding the fluid mechanics. And this is a very highly complex systems, and we simplify that and we look into the flow. Another natural thing that we observe, this system you can link it with your piping system, where we pump and then we supply the water in the different places and take the wastewater into the waste pond. It's probably the story of any campus, like including our IIT. So, this system also, this flow through pipes, flow through pumps, then flow coming through the brains and all these things, they will be all linked, and you can actually design these systems based on your knowledge in very elementary knowledge in fluid mechanics. It is not necessarily that you need this thing. This is one of the area in which my research lies, one of the area other than those vortex I saw, where you can see that people tried to see how this insects and birds fly. This is little early 2002. Today we know much better than that, lot of work goes on. And you can see over this wing there is a wrapped around vortex, and you can see this wake, there is some such flow, okay, the circulatory flow. This entire observation, this came in 2002 Nature publication. This entire observation was done in 2002, where this experiment is quite interesting. So, that is why just let me tell you a little bit about it. In a wind tunnel, they kept scented flowers, artificial flower, but they had such that a real butterfly will fly from one to other. And now, when a butterfly flies, you do not know whether it will fly from here to there or here to this flower, and there is a wind speed also. So, at that time they tried to observe this flow, and they used 13 cameras to visualize this. At that time, when they did this experiment, at that time to cover a cricket match, Channel 9 used to use 9 cameras. Okay. So, at that time they used 13 cameras to visualize this and to construct how the flow field look like around the butterfly wing. So, this is the kind of it actually shows the which direction research goes, which also actually shows that the application of fluid mechanics, where even in the biological system what we observe. You all see from flow from a pipe, when it comes out, it will be coming out very nicely, kind of thing. But if many of these engines, the exhaust are made with this kind of lobe nozzle. So, when you make like this, then it get mixed very nicely, and from the engines, when it particularly aircraft engines, when it comes out like that, then there is a lot of mixing. So, it will be less noise. So, it will be less detectable by the radar and all these things. So, this is how they mix the fluid like that. And this fluid, if you look into the flow cross section, so right now we are looking along, right now we are looking along the axis. If we make a cut, then what we are seeing, but if we take a cut in the xy plane here, then what you will be observing is something like this. Okay. So, at different location you will see very nice patterns, which eventually get mixed up at downstream. So, these like this you can have many examples relevant to your area, and you can actually try to motivate the students how they should go ahead with this kind of flow. Now, I wanted to show you some, also I show some videos, motivational videos or some educational videos, very short clips, so that some concept gets cleared. And unfortunately, my videos are not working here. So, I have to go out and play them. So, we all yeah. So, this is a flow, this kind of videos you will get. These are, I will show at the end the shorts. You can see this body is designed in such a way that it is initially very thin, and then slowly it is becoming bluff, like a thick. So, it is showing a difference between streamlined body and bluff body. So, when it is bluff, then there is a separation, or this, it is called separated flow in that region. When it is becoming streamlined body, then the flow is like along this body surface, and there is no separation. So, this is a video which shows the concept of streamlined body and this separated body. This is a simple concept. We all know that when fluid flows over any surface, because of viscosity, there will be no slip at the boundary. So, if you have to write an equation and say what should be velocity at the boundary, the velocity at the boundary will be 0. So, it is just a demonstration of that how the fluid particles will move. So, at the surface there will be stationary, and as it moves, so this velocities are less here and more there, it is the effect of viscosity. Same way, I usually there are two cars here. This is the sports car of 50s probably, but not today's, and this was the that time other models, because these videos were generated in that period. Now, if you see this region where this flow is disturbed, this is called wake behind this body, this is quite large in diameter, whereas the other one, the modern cars what you see mostly, this region is much less. So, this disturbed region or this wake region width indicates that how much drag this body will encounter. So, this car will be encountering much less drag compared to this. So, your mileage of this car will be much higher compared to this guy. Today modern cars will have even better efficiency, and if you see modern sports cars are all experiments are done, and wind tunnels and things like that. So, another example, we showed their laminar and turbulent. So, if you have a laminar flow, this dye, colored dye was moving very smoothly and nicely. If it is turbulent, it will be very random motion. So, this is how we introduce some of the concept to the students, and look at this picture carefully. That wingtip vortex, I showed the picture. So, it is that video of that, and so when the aircraft around this wing, there will be this wingtip vortex forming, and you can see sometime in the very clear sky winter days, because of the moisture condensation, those vortex lines in some places, okay, when the aircraft moves. So, this kind of videos are actually useful in terms of motivating the students these things. Sometime you like to tell them a little story, and I being in the aerospace department, I tell the story of Wright brothers, and the story of Wright brothers is in a very short brief. If I try to say, the story of Wright brothers are like they had a cycle shop, okay, and all the things that they have done is in their cycle shop, the design thing, okay. And this is, you can see the region their cycle shop or their warehouse where they were planning this design and all these things. So, first they built a flyer, this is good, and first attempt in they could not fly. Okay. That is 1901 or something. They made the design based on at that time available best theories, and whose theory it is? You all heard of NASA Langley. So, the Langley was that time the one of the scientists whose theory was well respected at that time, but most of these theories were kind of implicit in nature. So, Langley and Delinthan, one of the German engineer, their theory was respected most, and they built a aircraft based on that theory, and when they tried to fly, it did not fly. What they realized that the kind of lift it is producing, kind of lift to sustain this flight there it is producing is 1/3 of what they estimate, and they were so disappointed that they said in next 1000 years nobody is going to fly. So, that is their statement, that next 1000 years after their first failure, their statement was next 1000 years nobody is going to fly, and next year they flew there. Okay. What was the thing that they did that they could fly? They did not leave it there. Okay. So, they built the first wind tunnel at that time, a very small wind tunnel which is about 16 feet long, 1 foot cross section, and then they drove this with a fan, this wind flowing through that. At that time they did not have any modern equipment to measure these things. They probably did not have the things to make the model so nicely, but they made several models. In 1 year, how many models they tested? Any idea one can do? We all do some small BTF project, this that where the students will be making something and testing. Wright brothers in 1 year, how many models they made and tested? 50, 200 model they tested. And how did they measure the forces? Using this cycle, spoke and all, finally they have, it is like a measuring the weight. So, they placed weight in such a way that they can measure how much lift it is generating, how much drag it will encounter and things like that. And what did they found in this 1 year study? What they found is so simple that you will think, oh, it is so simple, but to do that they had to do this much effort they had to put. The wing they were using, if the length was this much, the aspect ratio, that means wing chord versus wing length, the span they were using was too small, and the theories were all for 2-dimensional theories. So, they realized that if they increase the length, then this edge effects will not be so important compared to the rest of the wing which is generating the lift force, which is according to 2-dimensional theory. So, what they had to change is from their earlier design is to increase the length of the wings, that is the wingspan. That aspect ratio thing to find, they figured it out and they flew next year, but just without figuring that out, before previous year they said that it is going to, nobody is going to fly 1000 years. And if you see this, this is the they used to measure the forces. They made their own balance, which we today use different force transducer, strain gauge based transducer and things like that, and they built them made this thing. So, such stories are, you can give such stories for many different things, like biological people, they probably can give the picture of a Leonardo da Vinci, where he has given the picture from the heart, how the flow is coming out and how the vortices are formed inside the heart, the blood is forming the recirculating flow and things like that. So, he started all this investigation long back. Unfortunately, after 300 years of after his death, all these pictures came out. These are only pictures because at that time we did not have the language of expressing them. So, these are like after the motivation, when we start the talk, we talk about the continuum, or the first question I asked to the student, what is a fluid particle? Okay. How do we define a fluid particle? The another question that we asked, the difference between fluid and solid. Okay. The fluid which cannot resist the shear force. So, if you leave it, it will flow. fluid will flow always. Okay. If you are not restricting it, then it will flow. But before that, I asked the question, what is the fluid particle, and here your physics knowledge of the class 12 will come in handy. If I take a gas, let us say, in a large volume or a small volume, wherever a gas we have taken, and look it under this microscope, take a tiny volume and look it under the microscope, and you find how many molecules are there inside that tiny volume. Okay. The density will define as mass of those molecules divided by that volume you have taken. Mass per unit volume is density. So, that is how you have defined for that. But if that volume under the microscope is too small, you may get sometime this value, sometime this value, or any intermediate values, because number of molecules can go, the number of molecules coming inside that small volume and number of molecules going out of that small volume need not to be same. Okay. So, that is why there is a critical volume such that number of molecules coming in that volume and number of molecules going out, probability of that is same. At that time we get a constant density, and this is what is the limit where we get the from microscopic observation to macroscopic observation we are going, and we define a fluid particle which should be of the order of delta V naught, where this delta V naught, this should be V naught, would be of the order of mean free path q. Because now here kinetic theory of gas we all do in the class 12, mean free path is the path between two molecules colliding. If I take a volume of a mean free path, the number of molecules, probability that number of molecules going out of this volume and probability number of molecule coming in is more or less same. So, then this volume is the critical volume in which I can say that it is, the density will be constant. If we have to do anything smaller volume than that, then we cannot use this continuum fluid mechanics that we all study, we have to use molecular theory. Okay. So, this is what we do in terms of the continuum thing, and if you see that delta V naught, it has about 10 to the power 9 molecules per millimeter cube in a the volume of delta V naught is of the order of 10 to the power minus 9 millimeter cube, sorry, volume is about 10 to the power minus 9 millimeter cube, and in that you have 3 into 10 to the power 7 number of molecules. So, it is a large number of molecules. So, even if you take a mean free path for a air, you have a sufficiently large number of molecules. So, the number of molecules going out or coming in will be same. So, this way when we teach this, then the students knows that there is a constant density, it is a continuum. But now, if I make this volume too big, then the body itself might have a different density, like in the sea water, as you go down the density is increasing. So, if my volume is too big, then the density will change again when this change the volume from one to another. This is called macroscopic uncertainty. So, all that we discuss is in this zone, where we are not under microscope and not under such large thing, we are in the continuum hypothesis is valid. So, beyond microscopic uncertainty we use. Okay. This part is macroscopic uncertainty and this part is called microscopic uncertainty. Now, why do we call this continuum? This volume is very small. So, I can take such volume and continue this and apply the properties of all continuous function. That means, all the differential relations and all this we can apply. So, that is why the differential calculus is so useful, and that is why we call this continuum hypothesis. Okay. Next, we talk about all these properties and other things, the dimensions and properties in a typical fluid dynamics course. I know it is really more involved for only for these things. Then we go into the fluid statics. Whenever we talk about the fluid static, what is the equation for hydrostatics? This is the equation that I will write for hydrostatics. Many of you will say that dp dy is equal to rho g and those kind of expression you will say. But usually when I will be deriving this 4 o'clock, no? 3:45 is okay. So, usually when we derive this, we will be deriving in such a fashion, I just need 5 minutes, okay. Such a fashion that you write it in the vector form, so that it is del p is equal to rho g. Okay. Same way when we talk about the fluid kinematics, this is another important thing, this is where the students get lost. That is what is material derivative, what is substantial derivative and things like that. I do not know whether it is already taught here, but if you see there, it is very important concept then what is local derivatives and what is material derivative. Now, if you take a fluid particle as it moves, this is at time t, this is at time t plus delta t, this is rho plus d rho, this is not visible here, and it has moved to d r distance. When you define rho as a function of x, y, z, t, all our second year students, all our undergraduate students, when they take fluid mechanics is probably third year or so, they have done the chain rule of partial differential equation, and you can write rho as this fashion, which we can write this term as del rho del t dt and this term as product of these two vectors, which is del rho dot dr. Dr is, if this is moving with velocity v, dr is v dt. So, you get this. So, when you are defining rho in the Eulerian frame of reference, Eulerian and Lagrangian, those who are teaching, all of you know, then actually the Lagrangian derivative is the local derivative plus the convective derivative. Okay. So, when you are following the material particle, then this is the derivative, but when you are defining at a fixed location or rho as a function of x, y, z and t, then this will be that derivative. Why it is required? Because when you do it for the velocity, replace rho by v, then you get acceleration, and when you apply Newton's law mass into acceleration, that can come only when you are for a fixed mass. Okay. So, when you do in Eulerian, you cannot see that fixed mass. So, this part should be made very clear, and one example that we do is like this, where if you see through a converging nozzle, the velocity at any point will be constant. So, that means dv dt is 0, but the acceleration is not 0. The fluid is velocity is increasing, so acceleration is not 0. So, then we talk about the streamline, strict line, path line. We talk about the Bernoulli's equation, and I think this Bernoulli's equation derivation you all should, we should do in terms of 3 methods: stream tube, Euler equation and energy equation. Okay. So, you can do it from the Euler equation part is very nicely written in the Facebook, and you can see that. Streamline derivation also is quite interesting, and you can see, and then we talk about the Reynolds transport theorem, okay. And then we talk about the dimensional analysis. Because of the shortage of time, I cannot speak everything, okay. And we talk about the potential flow. One thing in the potential flow that you must introduce is the flow between two plates or two lines, which usually is not talked about. Okay. So, if there is two plate like this, how will be the potential flow look like? Then we talk about the Navier-Stokes equation. This is my last slide. If you see most of this teaching, we are talking about using some video or some mathematical relations and things like that. Many of you will not be motivated with that, or many of the students will not be motivated with that. And today, a lot of students are coming in the universities, and to motivate them, now if you see that such education journals, not a single article describe experimental projects to support basic teaching. And this is where actually we are, I think the new generation of teaching will be coming, why we can do some simple experiments, like to show the Bernoulli's principle, how far it will go, or with the tank height, how this, because this will depend on this velocity here. So, how far it will go, you can actually note it down with a simple experiment like that, and you can explain the Bernoulli's principle. Now, this is where I have a small this thing. We are planning in TechKeep, as I talked with Professor Upadhyay, that we want to create such small modules, and those teachers who are interested to create, we probably have some program he will announce later, and then we will discuss that in the we want to create small modules, and it is not one person's job. So, if some people come, some people are interested, we will create such small modules of different principle of fluid dynamics to demonstrate, which can be done in a tabletop kind of arrangement. So, we have to think in not in this thing, because we cannot take 300 students there and demonstrate like this. It will be in the classroom demonstration kind of module. That is what we think of. Thank you.